Welcome to the Deep Dive, where we unpack the latest research making waves. Today we're diving into a really interesting paper called Compute as Teacher, turning inference compute into reference-free supervision. Thankfully, they call it CAT for short, and it tackles a core problem, right? How do you actually fine-tune these big language models for tricky skills, especially when you don't have human labels or clear right-wrong answers? Think about tasks where experts might even disagree.
Exactly. That's the supervision gap. And CAT's idea is, well, pretty neat. It takes the compute power you're already using during inference specifically, running multiple parallel rollouts or attempts, and turns that into a high-quality teaching signal without needing any reference answers. The key piece is this stable, frozen anchor policy. Let's call it Pi0. Pi and Ember looks at all the different attempts from the current model and synthesizes basically a single better reference answer by figuring out where the attempts went wrong or missed something.
And the results they show up front are quite compelling, aren't they? Using CAT, both just for better answers at test time and also for training. They call that CAT TRL. They got up to, 33% relative gains on math problems and 30% on health and voice tasks.
Yeah, across models like the newer Llama, Gemma, and Quinn models too, it shows the approach isn't just a one-off trick. It seems generally applicable, and again, crucially, without relying on human-labeled data.
Okay, let's dig in a bit. Why do we even need this? Set the stage for us. Why do the methods we already have, like supervised fine-tuning or standard RL, kind of break down for these non-verifiable tasks?
Sure. So think about standard post-training. You either do supervised fine-tuning, SFT, but that needs good examples, right? Labeled reference answers. Or you do reinforcement learning, RL, but that needs a clear reward signal, usually from some programmatic checker.
Like checking if code compiles.
Exactly. Code compilation, correct final answer in a math problem. Those are verifiable. But now think about generating, say, empathetic clinical guidance, or a really engaging dialogue, or maybe even writing poetry. There's no simple program to check, is this good?
Experts might disagree even.
Precisely. So SFT is out unless you spend a fortune on expert labels, which might not even agree, and RL is out because you can't write that simple checker. You're stuck. People sometimes try using another LLM as a judge, but that has its own well-known issues: bias, inconsistency.
Got it. So CAT comes in to fill that gap by essentially reusing compute you might already be spending. You mentioned group rollouts.
Yeah, that's a smart part of it. Many inference or RL techniques already generate multiple possible outputs in parallel for diversity or exploration, things like GRPO, grouped rollout policy optimization. CAT cleverly repurposes the output from that existing compute step.
Okay, so walk us through the CAT-T procedure itself. How does it work step by step?
Right. So two main phases. First is exploration. You take your current model, the one you're training, let's call it PITE, you give it a prompt to Q, and it generates, say, G different possible responses or rollouts. So you get O2, 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 OG, OG, AOG, DO2. These are just the model's attempts.
Okay, a bunch of attempts. Then comes the synthesis part.
Then comes the synthesis, and this is where that separate frozen anchor policy, PIDOLR, comes in. This anchor policy is key. It looks only at those rollouts, OGG, and a special synthesis prompt, importantly, it doesn't see the original question Q.
Ah, okay. Why is that important? That it's frozen and doesn't see the question?
Two critical reasons. It's frozen fixed because it needs to be a stable teacher throughout training. If your teacher keeps changing its mind, the student gets confused, right? The reference signal it produces would be unstable.
Makes sense.
And keeping it question blind, hiding the original prompt, forces it to reason across the different rollouts. It can't just ignore them and answer Q from scratch using its own knowledge. It has to compare $2, see where they differ, where they agree, what they missed, and synthesize a better answer. Based purely on that comparison, it decouples exploration from the synthesis or estimation step.
Right, it forces it to learn from the attempts rather than just trying again itself.
Right.
Okay, so now we have the synthesized references. How do you turn that into a reward signal for reinforcement learning, for KTRL?
Good question. This is where the approach splits based on the task domain. They have two main ways, or regimes.
Okay.
Regime 1 is for verifiable tasks. Think MATH-500, where there's a definite right answer. Here, it's pretty simple. The reward is basically just a binary check. Does a given rollout match the synthesized references? You use a lightweight checker, maybe just compare the final numeric answer strings or the boxed latex expression. Easy peasy.
Right, if Jones says the answer is 5 and rollout O also produced 5, you get a reward. Simple. But what about the harder case, the non-verifiable stuff like HealthBench? How do you get an objective reward there?
This is the clever bit, I think, for regime 2. Non-verifiable tasks, you can't just compare strings. So the anchor $Pi$ does an extra step. It takes its synthesized references and generates a self-proposed rubric based on it.
Wait, a rubric, so it's not just giving the answer, it's giving the marking scheme for that answer.
Exactly. That's a great way to put it. This rubric R is a set of, say, n-specific binary criteria, little yes-no questions that capture important aspects of the synthesized references.
Like what? Give me an example for, say, the health advice task.
Okay, so if inches was a good response to a patient query, the rubric criteria, $3 might be things like Criterion 1, does the response acknowledge the user's feelings? Yes, no. Criterion 2, does it suggest seeing a professional? Yes, no. Criterion 3, does it avoid giving definitive diagnoses? Yes, no. Concrete, checkable things.
Okay, I see. So you have these binary checks. Then what?
Then they use a separate independent LLM judge. Let's call it rollout owner. For each rollout O generated by the main policy owner, this pran judge just goes through the rubric R and checks. Does O satisfy criterion $R, yes or no? Does it satisfy $TOR, yes or no? And so on. The final reward for that rollout O, called ULODO, is just the fraction of criteria it satisfied. If it met 4 out of 5 criteria, the reward is, say, 0.8.
But hold on. You said earlier that using an LLM as a judge has problems like bias. Now we're using an LLM judge, Pranjondo, again. Doesn't that just reintroduce the same issues? Like, couldn't it still be biased towards longer answers or something?
That's the critical question and why this decomposition is important. Asking an LLM judge, rate this dialogue from 1 to 5 is really hard and prone to bias. The LLM has to make a complex, holistic judgment. It might latch on to surface features like length, but here the LLM judge isn't making a holistic judgment. It's answering a series of simple binary questions based on the self-proposed rubric. Does it acknowledge feelings? Yes, no. That's a much more constrained, verifiable task for the judge.
Ah, I see. So breaking it down into specific yes-no checks makes the judge's job easier and less susceptible to those holistic biases.
Exactly. It makes the reward signal much more structured, auditable, and stable. You mitigate things like inconsistency or reward hacking because the judgment is granular, not just one vague score. It shapes the reward in a much more useful way for the RL training loop.
Okay, that makes a lot of sense. Now let's get to something that really jumped out at me. Why go through all this trouble of synthesizing a new answer as? Couldn't you just, look at the initial G rollouts and pick the best one somehow, using selection methods like best of n or majority vote?
Right, that's the natural baseline to compare against.
Yeah.
And the paper argues synthesis is fundamentally more powerful than just selection or filtering. Why? Because synthesis allows for genuine error correction and can create an answer that's better than any of the individual rollouts. It's like an ensemble effect.
How so?
Imagine a math problem with 3 steps. Maybe rollout 1 gets steps 1 and 2 right, but messes up step 3. Rollout 2 gets steps 1 and 3 right, but misses step 2. A selection method might just pick one or average them poorly. But the synthesis mechanism run by the anchor Pider rulers can look at both, recognize the partial successes, reconcile the errors. Maybe it sees rollout 1 got step 2 right and rollout 2 got step 3 right, and combine them to construct the fully correct answer, an answer that didn't explicitly exist in any single oil ward.
Okay, and they had data showing this actually happens.
They did. On the MATH-500 dataset, they found that the synthesized references from CAT disagreed with the majority vote of the rollouts on about 14% of the questions. So it wasn't just following the crowd.
14% is quite a bit. But the really striking part was.
Yeah, this was fascinating. On roughly 1% of the math questions, the synthesized answer as was correct, even though it disagreed with every single one of the rollouts it was shown.
Wow, so it literally corrected mistakes that all the initial attempts made.
Exactly. That's strong evidence that CAT isn't just clever filtering, it's performing some kind of reasoning or synthesis that allows it to construct knowledge or solutions outside the distribution of the initial exploratory rollouts. True self-correction.
And this pays off in performance, right? Huh. How did CAT at inference time stack up against just picking the best rollout?
It was clearly better. Compared to just taking a single sample from the base model, using CAT for synthesis at inference time boosted scores by up to 27% on MATH-500 and 12.5% on HealthBench. It outperformed all the selection baselines they tried, simple sampling, picking based on perplexity, majority voting, etc.
So more compute in terms of rollouts generally leads to a better synthesized answer.
Generally, yes. The performance scales with G, the number of rollouts. More rollouts give the anchor more information, more diverse attempts, more contradictions to potentially resolve. It offers a nice practical trade-off. Spend more FLRPs at inference, get a better synthesized reference, which acts as better supervision. Although there's a small caveat. On the verifiable tasks like math, the benefit of more rollouts seems to keep going up. But on the very open-ended freeform tasks like HealthBench, they found the gains started to plateau relatively quickly, maybe around G = 4 rollouts.
Interesting. Maybe after a certain point, the rollouts just get too diverse or weird for the anchor to easily synthesize something coherent.
That could be it. Or perhaps the core disagreements are captured with just a few diverse samples on those kinds of tasks. It's an interesting detail.
Okay, so CAT generates a superior teaching signal.
Mm-hmm.
What happens when you plug this into the actual training loop, this CAT-TRL process? You mentioned those big gains earlier.
Right, up to plus 33% on math, plus 30% on HealthBench with Llama 3.18b. This is where the concept really shines, I think. You get this virtuous cycle.
Explain that.
So you start with your base model, PDLers. You use it as the anchor to generate synthesized references from its own rollouts. You use these as, or the rubrics derived from them, as rewards to train the policy, getting P$1. Now, P-1 is better than P-1. So when P-1 generates rollouts, those rollouts are, on average, higher quality. When the fixed anchor P-LR looks at these better rollouts, it can potentially synthesize an even more accurate references. This improved as is then used to train the policy further to get P-taller and so on.
Ah, I see. The student gets better, which helps the frozen teacher provide even better lessons. The quality of the self-generated supervision actually improves over time as the policy learns.
Exactly. The trained policy can surpass the quality of the initial teacher signal provided by PLROD's first estimates. It bootstraps itself.
And they showed this RL approach using the rubrics is actually better than just doing supervised learning on the synthesized answers.
Yes. Result 3 in the paper. KDRL, using those rubric-based rewards, consistently outperformed CAT SFT, where they just fine-tuned the model directly on the synthesized reference stringses.
Why do you think that is?
Well, RL optimizes for the policy that achieves the reward criteria, while SFT just tries to mimic the output string. Especially for complex tasks, optimizing for fulfilling those specific rubric criteria seems to be a more robust way to learn the desired behavior than just trying to match a single target sentence. It likely encourages more exploration around how to satisfy the criteria.
It all sounds incredibly promising, almost like a free lunch turn compute you already have into better models. But surely there are limits, right? Where does this self-improvement cycle eventually stop?
Absolutely, there are limits. They discuss this in the appendix. The main limitation comes from policy convergence. As the model gets better and better through CAT-TRL training, its outputs naturally become less diverse.
So the rollouts start looking more and more similar to each other.
Exactly. It becomes very confident and consistent in its hopefully good answers. But remember, CAT relies on disagreement and contradictions between the rollouts for the anchor PyDollars to find errors and synthesize improvements. If all the rollouts become identical because the policy has converged, there's no disagreement, no new information for the anchor to leverage. The synthesis step just reproduces the single answer everyone agrees on. The teacher signal effectively disappears.
So the process hits a ceiling based on the diversity generated by the current policy.
Precisely. The lack of sufficient diversity in rollouts from a highly converged policy puts a natural bound on this kind of reference-free improvement. The virtuous cycle runs out of fuel.
Okay, stepping back then. The big takeaway from compute as teacher seems to be this proof of concept. Inference compute can be effectively transformed into really valuable supervision, especially for those messy, non-verifiable tasks where getting human labels is a nightmare or just impossible.
Yeah, it's a very elegant way to leverage existing resources. It provides a concrete method for specializing models using self-generated signals, moving beyond the bottleneck of explicit human reference data. It's practical, it scales with compute, it's a solid contribution.
And it leaves us with a really interesting question to ponder, doesn't it? If CAT can, even occasionally, synthesize a correct answer that was better than any of the individual attempts it saw, that 1% self-correction finding, does this point towards a way to train models that can generate supervision exceeding human capabilities, moving beyond just mimicking human text?
That's the provocative thought, isn't it? If the model can identify and correct errors within its own generated possibilities, maybe it can bootstrap its way to understanding or skills that aren't explicitly present in its initial training data or human references. Of course, there's the diversity limitation we just discussed. Maybe future work needs to explore ways to actively maintain diversity in rollouts, even as the policy improves, or perhaps apply CAT not just to the final answer, but to the intermediate steps, the reasoning process itself. That could be a path toward genuinely novel capabilities.